So we've already done a lot of practice using free body diagrams to sketch out problems that relate to forces, and now let's take a look at some more applications of normal forces, friction, and rotated axes, and using those tools to help us solve problems. Rotated axes, you'll remember, we used initially when we had a truck going down a ramp carrying a circus cannon, and we found that solving the problem using a rotated axis was easier than using a normal axis we'd have aligned with the ground. So we'll revisit that problem and review that idea and then apply it to forces as well. So as you recall, normal forces we also call support forces. You're sitting in a chair right now, and the force pushing up back onto your butt we could call a normal force or a support force. In our simple case, with a book sitting on a table, we found that we have its weight acting downward and the table pushing back upward, and it's in static equilibrium, so it's not moving. So these forces have to add up to zero according to Newton's first and second laws. So the simple question I ask is, normal force always equal to the object's weight? Well, we're going to come up with a couple examples here to prove that this is certainly false. So you've got to be careful about understanding what the values of normal forces are and think about this. And if you draw a correct free body diagram, you will figure this out on your own. So also keep in mind, remember these items that I've listed up here. Remember, a normal force is just two objects that are touching each other, and they're going to act on each other. They're going to push against each other. And so it's how hard they're pushing against each other. The direction of that pushing force is going to be perpendicular to the surface that the object touches. So if one object is curved and you have an object touching that curved surface, then draw a tangent to that point, and your normal force will act backward against that tangent that you did, perpendicular to the tangent. And how do you measure that force acting between two objects? Remember, that's a pushing force or a compression force, so use a compression scale. So let's take a look at a problem here. And what we've got is a 150-pound person standing still being pulled on by a rope. And we actually did this in class, so somebody was clever enough to figure out that there's something we could do to change our normal force. So we've got that person standing on the ground, you've tied a rope around their waist, and you're pulling somewhat upward at a 30-degree angle with a fair amount of force, 100 pounds of force. So the question is, can you find all the forces? And we're going to use the 5-step process to solve this problem. And let's just see what happens with all of our forces, including in particular our normal force and our frictional forces. So what we're going to do, remember a free body diagram, we take the object, freeze everything around it, and then draw all the forces acting on that object only. And so our first force, of course, I'll put in gravity. So we've got gravity acting downward with 150 pounds. And of course, the floor is pushing back up on the person, so that's a normal force. And the problem is, what is that value? Don't jump to a conclusion that it's 150 pounds. Let's let the problem solve for itself and figure out what it is. What other forces are pushing or pulling on this person? Well, we've got a rope. Somebody's yanking up with a rope tied to their belt or something with 100 pounds. I also gave a direction on this of 30 degrees. Finally, if these were the only forces acting on this object, then we would not be standing still because I have an unbalanced force yanking us to the right. So we've got to have something counterbalancing us to the left to keep us still. And what is that? Well, that's your sneakers on the floor rubbing against the floor. You've got frictional force acting to the left, opposing that intended motion. Alright, so we've got frictional force. And what type of frictional force? There's two types. There's static and kinetic friction. This one is static friction because we're not moving. So the next step in a process, when we have a diagram which has vectors in it, and we're eventually going to add these up, so we need to break them down to x and y components so we can add up all the x's, add up all the y's, and see what happens. And so here we go. So we've got our x component of the tension in the rope, and we've got the y component of the tension in the rope. Now, how do we get these values? Given that we have a number here, how do we calculate the values? Well, I've got a 30-degree angle here, so of course there's two ways to do this. The easy way is to use a special right triangle, which I would expect you to jump on very quickly to do that. The nearly as easy way is just use SOHCAHTOA. I'll warn you right now, This is a right triangle, so we do not need to use law sines and law cosines to solve a right triangle. Those are special tools used to solve for non-right triangles. They will work on right triangles, but it takes extra time, and why would you want to take up extra time? So if you use the wrong tools for the job, expect me to take off some points, because you're going to be wasting time, and I'm trying to focus you on using the most efficient ways of solving these things and not doing things that are a little bit crazy. So go ahead and use SOHCAHTOA if you want. Remember, we've got the opposite and adjacent, and the opposite gets us the y value of this, as long as we're in a standard position here. And that's 50 pounds, which is, of course, that makes sense with the 30, 60, 90 triangle. The short side is half the hypotenuse. And the longer side is square root of 3 times that half, which is 0.8660 times that, and we get 100 pounds times 0.866 is 87 pounds, roughly speaking. Now you'll notice I just made my original vector disappear. If we kept that vector in here, that would mean that we would have that vector plus all these others acting on the object. Well, we don't. We're replacing the non-aligned vector with two aligned vectors in the x and y directions. So it's best if you either very lightly draw that one and make sure these are much, much heavier, so these are the ones that focus on, or to get rid of that one altogether after the fact. And so these are our decomposed vectors, and I'm just going to move maybe this over to the side here so you can see I've got 3 vectors acting in the y direction, and I've got 2 acting in the x direction. And remember, the object, the person, is not moving, so we're in static equilibrium in both these directions as well. So there's our first 2 steps of the 5-step process. Now let's identify what we need to find. Well, we need to find all the forces. Any assumptions that we need to make? No assumptions that we need to make for this type of problem. So that's step 3. So we've identified what we need to find. In fact, here they are right here. We need to find the normal force and the frictional force. We do know these 2 forces are tension force, which we've broken down, and our gravitational force. Step 4, write down equations that apply to the situation and what relationships apply. Well, one relationship, folks, when you have a free body diagram. Sometimes you'll also use Newton's third law as well, but Newton's second law is the go-to for these types of things. I typically use Newton's second law rather than Newton's first law, because Newton's second law is a more general approach to it, and you'll see in a second what I mean by that. Now, you notice I've drawn this in purple because this covers forces regardless of the directions, and what I'm going to do is I'll break this down into solving for what's going on in the y direction and then solving for what's going on in the x direction. And I'd expect you to lay out your work in a very similar fashion. This is very well organized, and it's very easy to follow for anybody looking at your work. And if you don't follow this, you can expect to lose points. So here's our directions associated with this. And what we're going to do is let's go ahead and we're going to plug in for what our forces are over on the left side. So we'll have to add up all the forces, stick them right here. And the right side, we can plug in things that we know about this. And of course, I'm going to start, I think, with the right side on this. What do we know about acceleration in the x and y direction for this situation? This is going back to ask the question, what do we know about the equilibrium situation from Newton's first law? And this object is not moving at all, so both in the x direction and the y direction, our acceleration is 0. We're not moving at all, so I'm going to 0 those out. And I'll just make a note to myself why I'm doing that in static equilibrium. And now I'll go ahead and start plugging in to the left side of the equation. Left side of the equation, we add up all of our forces. In the y direction, I'll start with the y's. We've got 1, 2, 3 forces showing up on our diagram. So I'm going to put 1, 2, 3 forces right in the left side of the equation. And here they are. And remember, the way we do this is we use a sign to represent the direction, and then the magnitude is the size of the arrow itself, the force. So I've got a downward force due to gravity, I've got an upward normal force, and I've got an upward tension force, one component of the tension. And that has to equal 0. Our unknown here is our normal force. We actually know what Fg is and Fty are. So I'm going to go ahead and keep this as a general solution for now. And I'm going to solve for Fn. But this, I require that you go to this point at least before you start plugging numbers in. Better yet is to solve for your unknown as a general solution before you start plugging things in, typically. Sometimes it gets a little bit cumbersome to do this, but generally speaking, I like to do general solutions. So here's our general solution for our normal force. In terms of our knowns, we know what Fg is, we know what Fty is. And if you wanted to make a little bit more general, instead of Fty is, you could plug in Ft sine of 30, because a true general solution is actually comprised of our given information from up front. And we were given 150 pounds for Fg, we were given Ft, and we were given our sine and our angle, should I say. So let me go ahead and plug in some values here. So we've got our gravitational force offset by 50 pounds of upward pull by our tension, which is equal to our normal force. Well, that actually makes sense. We've got three forces here acting in the y direction. They have to add up to 0. So Fn cannot equal Fg if that's going to be the case. We know that Fty is up 50, Fg is down 150, so this has to be upward of 100. So that's proof that normal force does not, generally speaking, equal our gravitational force. Let's just see what's happening in the y direction now. I've plugged in some values for my normal force here just so you can see we've done that. So now let's focus on finding our frictional force. So to find our frictional force, let's go ahead and apply Newton's second law again. Here's the x component. And once again, we're not moving the x direction either, so I'm going to zero out my acceleration, so static equilibrium. And as I said before, I don't really use Newton's first law immediately. I typically apply Newton's second law, then zero out the acceleration if it is a first law situation. And once again, I'm going to plug in all my forces on the left side of my equation. There's two forces I've got to the right in the positive direction, Ftx, and then in the negative direction I've got Ff. And now I can go ahead and let's solve for our unknown here, which is the Ff. I'll just shift the Ftx over to the other side and get rid of my negatives. So pretty obvious, right? If these two have to add up to 0, they're equal and opposite. So I'm just showing here that my magnitudes are equal. And so my Ff equals Ftx, which we've already solved for, is 87 pounds. And once again, if you were to want to express this as a general solution, Ff actually equals Ft cosine of my theta, 30 degrees. So there's our solution to our problem. One more question you could ask yourself is, if a bathroom scale was placed under the box, it would read what value? Well, bathroom scales are good ways to measure normal forces, right? They're compression scales, and normal force is how hard two objects press against each other. Perfect job for a bathroom scale or a compression scale more generally. So that should read 100 pounds. So we've just given a counterexample to our true-false question to show that no, Fn does not equal Fg always, because we actually had three components that are acting in the y direction. So how can three things add up to 0 if two of them are the same? It's impossible. All right, so we've got we can't have 150 upward and 150 downward when we've got another 50 pounds from the y component of my tension force pulling upward. So that offsets my normal force. Let's just step back for a moment, and I asked you to do some reading, and we've already done a lab on friction, and the readings should support your ideas behind that lab, and you should make sure that you answer all of these questions. And we're going to be using some of these ideas coming up here, and so I just wanted to touch upon some of the key ideas that you should have picked up in your notes. Your notes for your reading, which was a 2 or 3 page section out of your book, should be very visually oriented, looking at a diagram or two, maybe an example, and showing what key equations pop out, key relationships that pop out from these ideas, and maybe a few bullets defining things and outlining what's happening. So I would imagine this take more than half a page, and certainly these questions should be answered as part of that. So make sure this is done. So let's step back for a moment and go back in time and look at our circus cannon driving down a hill. The reason I wanted to go back through this again, number one, is that you've got to remember how to solve free fall problems, or generally speaking, kinematic motion problems, where we use our kinematic equations to solve for the motion of objects and the position and velocity and acceleration at any time for objects under constant acceleration. So, but more importantly, it refreshes our memory on rotated axes. So let's just go through this quickly and refresh our memory on this. Let's take a look at another problem here. Now we've got a box sitting on a ramp. Well, what a surprise. So what I'm going to do here is I'd like to figure out all of the forces acting on this box and see what's happening with the box. And so it's a 22-pound box. I gave you the weight of the box in messy US units, and you can convert those pretty easily to kilograms for a mass if you'd like. But in the x and y direction, we're in static equilibrium. We're not moving. And so the sum of the forces in the x direction should be 0, and the sum of the forces in the y direction should also be 0. And so let's draw a free body diagram. So what I'm going to do here is I'm going to draw my force due to gravity first. And a little trick for you here. When you've got something on a ramp like this, draw the gravitational, or draw your whatever downward force you have, or acceleration, or whatever it is, from the surface of the ramp all the way down to the edge, because it gives you another right triangle here that you can hopefully see, and it'll help you sketch out your decomposed vectors later on when you need those. So second force acting perpendicular to the ramp, because that's what normal forces do. We've got a normal force pushing up off the ramp that's perpendicular to the surface of the ramp, as all normal forces are, perpendicular to the surface. And if these were the only two vectors acting on this object, what would the object do? Well, are these balanced forces here? No, we've got a force pulling downward and a force pulling up and to the right. So if we had a force downward and upward, they could potentially cancel each other out. But there's absolutely no way two forces like this could cancel out. In fact, I'd have to have some sort of motion over somewhere in this direction in the quadrant 1-4 area. And so let's take a look and see what that is. This is just a reminder how to draw our normal forces. And the other question, of course, we're trying to ask here is what's the size of these normal forces? So we're going to take a look at that as well. I'm not sure why I have an S here. That just should be Fn. So these cannot be the only two forces acting in this box. Otherwise, this thing would not be in equilibrium. It'd be sliding somewhere down this way. So what we're going to do is let's just add up these two forces and see what the total of these two are, and then we'd see what total force is acting in this box. If we didn't have a third force in here, that's the total of these two, and we'd be sliding down the ramp. So we've got to have something that opposes that to give us equilibrium here. So what do? That's our total force of these. That's our net force. So we've got to have a third force that would counteract this force to keep us in equilibrium. And so what we can do is we could actually take this third force and we could flip it around. So these three forces, 1, 2, 3, add up to 0. And now we're in equilibrium in both the x and the y direction. All right. I did this without doing any decompositions, and typically what you'd do is you'd work out some sort of vector decomposition here, which I'll do next. But these three forces are what's going to act. The question is, what is this mysterious force here acting up the ramp? Well, that's friction. All right. Okay. So there's our three forces acting on this, and if we wanted to formally go through and add these up, we'd want to decompose the vectors and break them down. And are there any lessons to be learned from the circus canon? Well, look at this. We've got three vectors, and if we were to want to break these down into some of the forces in the x and y direction, if we were to take traditional axes that line up with our ramp, the horizontal and perpendicular forces of a ramp, we would have to break down these two vectors, and this would be the one that would be an easy one because it's only in the y direction. But once again, we have two vectors that are perpendicular to each other here, and so if we rotate our axis to line up with these two, then we could keep these two as easy vectors and have to just decompose this 1/4 due to gravity, which is what we'll do. So here's our orientation that we're going to pick. Rather than using the ground and the side of the ramp, we're going to use the surface of the ramp, and we're going to use this line that's perpendicular to the ramp. Does that look perpendicular? I might be a little bit off with my sketch here. So my normal force is lined up with a perpendicular, and my frictional force is lined up with a horizontal portion, the x portion. And I've got positive x to the right, and I've got plus x upward. Now the only force we have to decompose is our force due to gravity. So we're going to do that right now. And you'll notice that we are now aligned with these, so I can change these colors to match up with my colors. So this is now a Y component, this is an X component. And I hope I fly in someplace here an XY axis. If I don't, you should draw off the side. Well, I do here. It's my XY axis. I haven't drawn large quantities here. Don't fool myself. So I need to decompose my force due to gravity into this structure here. I've got my X and Y components. And so I've got a downward portion of this and a rightward portion of this right here and here. And so here's my angle once again. I already showed you the geometry before. That angle down here matches that from geometry. You should know how to figure that out. Here's the downward piece and here's the rightward piece. Very easy decomposition. And then we can use SOHCAHTOA to break this down. And this is the opposite side. So our X component is our gravity, which is mass times gravity times sine of the angle, theta. And our perpendicular component here, our Y component, is mg cosine of theta, which is the adjacent side. All right, so there's our decomposition. If we go ahead and start plugging things into our equations, well, first of all, we're not moving at all in the ramp, so both the accelerations, the x and y, will be 0 because we're in static equilibrium. And now I can add up all my forces in the x direction. I've got my frictional force acting in the negative x direction. I've got my gravitational component in the y direction. I mean in the positive direction. And so those pop in right here. Those have to equal 0. And let's assume that I know what my mass is. I do here for my box. It's a 20 kilogram box. And so I'm going to solve for my frictional force, is my unknown. And my frictional force equals mass times gravity times the sine of theta as a general solution. And in the y direction, I can do the same. I'm not moving in the y direction. We're static equilibrium. My forces, I've got two forces in the y direction. I've got my negative component of my gravity, and I've got my positive normal force, and we're trying to figure out what this unknown normal force is. And so my normal force is equal to my y component only of my force due to gravity, so it's mg cosine of theta. Once again, this goes back to answer that important true-false question. Does the normal force always equal the force due to gravity? Well, no, it doesn't. Here's another example. So we've rotated our axes to line up with our two perpendicular forces, and we only had to decompose one, and we went through the process of applying Newton's laws. This is the standard process we'll use over and over again, and at this point we could start plugging in some knowns and work out actual numbers to the problem if you'd like to, so feel free to do that. So here you go. I'm going to plug in numbers for you here just to show you a numerical version of this. And so plugging in numbers over here for mg cosine of theta, we have 86.6 newtons or 87 newtons in the y direction for the force due to gravity in the y direction, and that's going to equal our normal force. It's 86.6 newtons, not the 100 newton force that you have acting due to gravity. Only a portion of it goes into a normal force, because the other portion of gravity is pulling me down the ramp, or trying to pull me down the ramp at least. So in the x direction, this 50 newtons that's acting down the ramp, if you work out the numbers here, and remember this is a 30, 60, 90 triangle, so you don't need to use the SOHCAHTOA. You can just use the special right triangle rules. So this 50 newtons acting down the ramp, because we're not moving, has to be equal opposite to our frictional force, our static frictional force up here of 50 newtons. And so those are our numbers for this problem. So there you have it. So once again, does our normal force always equal the force due to gravity? Absolutely not. So here's another example where normal force is not equal to force due to gravity. And once again, for the same reason that we had a problem before where we had two up and down forces with a third force off to an angle, that means the normal force is going to have a component of this along with gravity adding up to offset it, just as here our normal force is not going to equal gravity, but one of the components of gravity to offset it. So normal force does not equal Fg in all cases. Okay, so this is an interesting bonus. In all three of the scenarios that we've gone through with normal forces, gravity has always been integrally involved with those normal forces, but they don't necessarily equal the gravitational force. My question is, can you come up with some examples? And you can post online one example, and you'll get one chance at this. And there are many examples out there, so many people can get a bonus point for this. Of an example where gravity has absolutely nothing to do with a normal force acting on an object. So think about that. See if you can come up with some examples and post them. And they've got to be unique examples. So if somebody gives an example, you can't give something that's a slight variation of it. So as a homework activity, I already provided this page to you. You may not have these two at 30 and 60 degrees. Please add them in if you don't have those on your worksheet. And what you want to do is draw a little free body diagram for each one of these. I've got a skier skiing down a really slippery, weird hill here. And so I want to know what the normal force is in each one of these situations. So finish up these little free body diagrams and break down your normal force. And what you'll do is do a little rotated axis in each case and break things down. So, for example, in this first case, I have force due to gravity acting downward, and I have the normal force that will be acting upward at 150 pounds. That's our simplest situation. And as we slide down this crazy hill, I want you to figure out what the normal force is in each case. And the only force acting on this, external force acting on the skier, is gravity, and then you're going to have to draw on the rest of the forces acting on. My sheet sort of looks like this when I'm going to do my solution, because I'm just replacing the skier with a simple object. But you can go ahead and draw it right on as the skier itself. So draw a gravitational force acting on each one straight down, and then I want you to figure out the normal force for each one. And then so little questions. You can just follow this little simple set of questions I had. And if your version of the worksheet doesn't have these questions, write them out and just answer those. So you should have this full-size page in your notes that I handed out. Now let's revisit the same problem, and we're going to let the box now, same box, same ramp, let it slide down the ramp with a constant velocity. So let's just see what happens here. How does that differ from the last one? Still got gravity acting downward, and we can break it down as we did before. We're using a rotated axis. And I'm going to go ahead and use numbers on this so we can look at numerical results. So we've got 50 newtons of force acting down the ramp, and we've got 86.6 newtons acting into the ramp. What's happening in the x and y direction? Well, in the y direction, we're in static equilibrium again. And so we've got to have equal opposite forces here. So I've got to have 86.6 into the ramp and 86.6 up in the ramp. Otherwise, we'd be accelerating either this way or that way. So these got to be equal opposite, these two components. And once again, we're moving at constant velocity down the ramp here, and so in that direction, in the x direction, we are moving with a constant velocity, which means we are in dynamic equilibrium, Newton's first law, still down the ramp, which means our kinetic friction, remember we're sliding now, so this is kinetic friction, must equal 50 to counteract that 50, because these have to add up 0 if we're at constant velocity. Remember, Newton's first law, an object in motion tends to stay in motion with a constant velocity if all the external forces add to 0. And so these have to add to 0. Now, you might ask yourself a question, and this is a really interesting question and an important question. All right, here's my equations. I should have flown these in a slightly different order here. Okay, so those are the equations that match up with these. Sorry about that. So here's what might be bugging you. It would bug me until I figured this out. I told you this is the same exact ramp at the same exact box that we had before for problem 27b. And the question is, if it's the same exact ramp, the same exact box, how could I possibly be moving down this ramp with a constant velocity under the same conditions, where I have the same exact kinetic friction force as the static friction force? As we worked out in our lab, and you read in the book, that our static friction force is, generally speaking, bigger than our kinetic friction force. So something weird is happening here, or more importantly, you've got to reread your notes and figure out why this is possible. If somebody can explain and give me a clear, concise explanation of why this is before I cover it in class, you get one chance to do this online, and I'll say yes or no. Go ahead and try that out, and I'll give bonus points, 2 bonus points for the first person to answer this one. This one's worth 2 bonus points. So, in other words, this is possible. So there is a good explanation for it. So help me out and find it. So what if we take the same problem that we had before? Now, what if the box happens to be speeding up? Well, can we actually use the same exact conditions that we had before, or are we going to have to change something to do this? So let's just take a look at what the vectors would look like for this. So same gravity acting on the box. So we've got 50 newtons acting down the ramp, and we've got 86.6 acting into the ramp. And because we're in static equilibrium in the y direction, we have to have these two equal and opposite. All right. So in order for us to be speeding up down the ramp, we've got to be in an unbalanced situation here. So we can't be in equilibrium, which means if we have 50 newtons down the ramp and we're accelerating down the ramp, this has to be a larger force than our frictional force acting up the ramp. So in the past, though, remember, I was showing you in the previous 2 examples that our kinetic and our static friction force in the last 2 examples were 50. So it is not possible to speed up if this is the case. And so my question to you is, we're going to have a constant kinetic friction force of 50 newtons unless one of two things change. And so what two things could change, and either one could change in order for this situation to change. So I'll let you try to answer this bonus. But basically, if we do have a situation where this is speeding up down the ramp, this would have to be a smaller vector here, maybe a 25 newton vector. And the question is, what could we do to change that? Similar situation for number 30. What would the free body diagram look like if this was sliding down the ramp but slowing down? All right, so same breakdown that we have here. We have our equal opposite forces here, and we've got a 50 newton force acting down the ramp, our component of gravity pulling us down the ramp. So if we are slowing down, that means we're not in equilibrium, so we've got a non-equilibrium situation. And if we're moving down the ramp but slowing down, our acceleration has to be pointing up the ramp, which means our net force in the x direction has to be acting up the ramp. So if we have 50 newtons acting down the ramp, we better have something somewhat less than 50 newtons acting up the ramp. So maybe we'd have, something more than 50 newtons acting up the ramp. So maybe we'd have 60 or 70 newtons acting up the ramp to slow us down. And the question is, once again, what changes could I make the ramp to make something like this happen? Here's a couple of questions we're going to answer in class. I'd go ahead and maybe take a moment to get your vote together on this question. I've got a situation here, a little free body diagram. Describe the motion. So have your votes ready for this in class. You've got a description of the motion, generally speaking, stationary, constant velocity, accelerating. Could be both of those, 1 and 2, or maybe none of these. And then I want you also to describe which direction is this object moving in. And that'll be one of your votes. And then I'm going to use this very similar situation here. Same questions, and here's the new free body diagram, and now answer those same questions. A second homework assignment is this, and this is actually a question directly out of your friction lab. It's for experiment number 2. This is a pre-lab activity you have to do. You have to do an analysis of the situation, predict what will happen, and then we'll actually test it. So we have an object sitting on a ramp, and what if we were to increase the angle to increase the height of the object? So we're going to crank this make this steeper and steeper and steeper. The question is, at what angle would we have this before the block actually begins to slide? Now you actually have collected from the first part of your lab your static coefficient and kinetic coefficient of friction, and you should be able to predict that. But when you work this out, work out a general solution first, and then you can actually plug in your numbers and make a prediction what that angle is and actually test it in class. So what I want you to do is work out your first run of the problem right here. And it's a pretty easy problem to work out. Just push yourself through the 5-step process, and as you go through the 5-step process, your answer will drop right out, and it'll be a really simple and interesting answer you get. and figure out what angle it takes to actually cause us to start to move.